Hello, welcome back to another video. Today we're going to be continuing our talk on smart pointers. We're going to be going over the drop trait that a smart pointer can implement, and that gets called anytime that a smart pointer goes out of scope. So if we had like let x equals some smart pointer and we reach the end of our main, then drop is called here for x. So we'll go over the drop trait, and then we're also going to go over reference counters. And reference counters allow us to basically say let a equals c, and then we could say let b equal a, and also let c equal a. It allows us to kind of use um, B and C as, or let C, our character C, have multiple owners like B and C. Even though this is a scalar type, just pretend that this is a pointer. So without ado, let's get into it. Okay, so I just copied and pasted this example from the textbook into my editor here, and we'll go over it real quick. So we're just declaring a custom smart pointer, and we're not actually pointing to anything on the stat, or the heap, I should say, in this case, but and all we're doing for this case is implementing the drop trait. We're not doing deref stuff, so it's a pretty basic pointer. So it's just containing some value, and right here we're gonna implement the drop. We have drop here, and we're allowed to mutate self because this is allowing us to do any cleanup operations. So when we would want to implement the drop trait on a pointer is if we're doing like some cleanup stuff. So like a good example would be if this was like a file, this could like close the file handler. This could close our network socket. It could do a bunch of different things. Or unbind our program from a socket, right? So in this case, we're just going ahead and printing, oh, we're dropping it. So we, in our main here, we declared our custom smart pointer with some stuff, and they got created. And as you can guess, we're gonna run this dropping custom smart pointer at the end of our main. Once I cd into smart pointers, and as you can see, it kind of drops in order that we don't expect. It drops it in from the most recently accessed pointer first, then the least accessed one. So other stuff gets dropped first, followed by stuff. I could go ahead and declare this in its own special scope right here. So, well, I'll actually do that with my stuff. And that way we'll see now my stuff gets dropped before other stuff. So we allocate C here. C.drop is called. And then down here at the end of main, D.drop is called. Go ahead and run this. As you can see, my stuff is dropped first, and other stuff is dropped after our print message right there. For some reason, we want to drop a value, a smart pointer, before the compiler automatically does it when the owner goes out of scope. So again, C went out of scope here, so it gets called. We don't do something like C.drop. We don't do that because that just runs the cleanup that we wrote. It doesn't actually mark C as invalid reference or invalid variable anymore to this custom smart pointer. Instead, C we run our cleanup logic, but everything is still fine and dandy in the Rust compiler side of things, and the Rust compiler says, oh, I found this C, so it's going to call c.drop again when C actually goes out of scope. So if we actually wanted to drop it and have Rust, or let Rust know that, hey, this value C is no longer valid, then we call something standard mem drop. We do that on C instead of calling the drop method on C itself, or whatever our custom smart pointer is. So I'll go ahead and show this in action and remove this outer scope. So now we're calling drop on C through the memory module instead of calling drop on the drop method on C. Internally, this drop does indeed call c.drop, but it also marks C as invalid and expires its lifetime. So if I go ahead and do cargo run again, as you can see, dropping my stuff first before other stuff. So that's it for drop. It's pretty self-explanatory, and again, just gets called when a variable goes out of scope and or the owner goes out of scope, and we can also call drop manually through this standard memory module. Next up, the reference counter. To start with that, let's take a look at an example graph. I'll go ahead and switch over there. So let's say we're trying to create a graph like this, where we have node A pointing to node B, and node A also points to C, and then B also points to C. Now, your first thought is something like, well, why don't we just pass references to node C for A and B? And because, again, we want A to have some sort of connection to C, and we want B to have some sort of connection to C. And with what we know with Rust so far, only one variable, or only a value can only have one owner, right? So it might make sense to pass references, but if we start building out our graph with references, you can see that's going to get hairy pretty quickly. So I'll go ahead and just restart our binary crate here, and let's try declaring a node that holds a reference to another node, right? So, or a vector of nodes. So I'll do struct node, and we want to specify the lifetime A here, and then we can have a value. This is what the value is going to be in our node, so I'll just pass in a number, and then we'll say that the nodes that we want to reference to it's going to be a collection, a vector of references to nodes that at least have the lifetime A node, and we'll pass in at least the lifetime A to any descendants of nodes. So it kind of works recursively, and in this case we're basically saying that as soon as one node in this chain of nodes becomes invalid, invalidate everything else up the chain, if that makes sense. So we're saying if C becomes invalid, then A becomes invalid, and also because B points to C, B will become invalid as well. Now, I went ahead and tried to make a create graph function that takes in a lifetime A and tries to return a node with a lifetime A, and I went ahead and set up our graph here with A, B, and C like so, and then I returned the head of the graph A, but of course this isn't going to work because B and C are declared within this create graph, and so is A, but we're returning ownership of A, so that's fine. But B and C are created within our create graph function here, and they go out of scope right after this function ends. So It's really hard to work with references when it comes to graphs. We have to have all of our nodes within the same scope of each other, and it makes it real tough passing around uh, graphs. We could like clone everything, but then that's just a pain in the butt, right? Or we could do pass everything like A, B, and C back, but like that's not very friendly to us as a developer, right? So uh, as you can see, the referencing nodes uh, in using lifetimes is going to limit us pretty heavily in terms of what we can do. Uh, so on second thought, we might be thinking, well, why not make this a box, right? Like, why not say that we own a box of nodes? That seems to make sense, right? So that way we're not creating a recursive reference to node within our struct node. We're not doing something like node nodes, which would be very bad. We're doing instead a box of nodes, and we're providing some indirection, and I should actually write it correctly. And we also don't need this lifetime specifier anymore. So let's try and go ahead and refactor this with boxes real quick. Okay, great. So this fixed our first problem, which was, hey, we created B and C, and we were passing references to them, and they no longer exist after the end of our function with lifetime specifiers and just plain old references. But by putting them on the heap, we're able to point to them on the heap, and all is fine and well when we return. But now we run into a new problem. As you can see, pardon the pun, we're trying to own the value of C twice. So box, the constructor of box takes ownership of B here. So we're actually owning box.new is owning C here, and then C is now invalid after this box new call, and we try calling it again. So it would be pretty silly to try to fix this by doing something like c.clone. The clone would go up here, but why would we want to have multiple copies of our nodes floating around in our graph? That would be terribly confusing. That's where this smart pointer RC comes in. RC, also known as reference counter, allows us to bend the conventional rules of ownership just a little bit and gives us the ability to have multiple quote unquote owners of C. So let's go ahead and fix our code with the reference counter real quick. So first of all, I'm going to go ahead and bring RC into scope by using standard reference counter. And then second of all, we're going to just allow debug on node so that we can work with that later. So I'm going to derive debug, and then what we're going to do for nodes, we're still going to have a vector. We're still going to have a vector of nodes, but instead of it being a box, we're going to have reference counter. And now we need to fix our nodes definitions here. So I'll go ahead and instead of box new, we're going to do, and not clone it, that was just for demonstration purposes. I'm going to do, instead of box new, RC clone B and C. And we're also going to wrap these within RC new constructors. I'll let A be in this case because we're not using A for anything else. And then we're going to pass in references so we don't mess up ownership. So let's go by this line by line what just happened. So instead of creating, well, we did create a node, but what we did is we wrapped it within a reference counter. So again, our reference counter is just a smart pointer, and a smart pointer is literally just a reference with fancy metadata and methods on it. So we have now a new reference to a node, and we're basically saying RC gets treated a little bit in a special manner. We can assign C to RC.node, but that means that the strong reference count, as long as the reference count to whatever this RC new is above 0, it's going to remain valid and in memory. So in this case, we have C references this node with a value of 3, so our strong reference count is going to equal 1. And we went ahead here, and with B, we did the same thing. We created a new smart pointer to a node, and that node has the value of 2, but it also points, now in this case, this increases our strong reference count by 1. So, and again, we're not passing ownership here so that we can create more and more strong references. I know it's a little bit confusing, but at this point, we now have B with a value of 2, and its strong ref count is 1, and then B.nodes 0, or should I just say C, our node C, which has a value of 3, now has a strong count of 2 because C is referenced by the C value itself, and through this rc.clone, B has ownership of a strong reference to C, if that makes sense. And then finally, we'll go to our A value here, and we assigned it the value of 1, but then we also passed in, just like our like in our diagram that we showed, we're getting a strong reference to B, and we're getting a strong reference to C. So now we can say strong ref A has a strong ref count of 1 in this case because it has, well, actually A doesn't have any strong references because we didn't wrap it in an RC pointer, right? So technically A is just a node and doesn't reference or have any strong references to it. It just is owned. And then we have B, which now its strong reference count is 2 because we referenced B up here through the B variable, and then we made a clone of it, or we created a strong reference to it through here. And again, vector is going to own this this newly created strong reference, as you can see. And then we can say that C, now its reference count incremented by 1, so now C's reference count is going to be 3, and we can return A here because it matches its definition of a node perfectly. We have a vector of reference counters to nodes here, and one sec. And since we have these strong reference counts to B and C via here and here, B and C can actually now even though they're owned, they can go out of scope, and they're kind of treated like box in this way, right? Where the original owner of the value, this got copied onto the heap actually, so B and C can become invalid, but since we have strong reference counts still to these wrapped nodes, the values themselves don't go out of scope or leave memory or become invalid. We still have valid references to B through A, and we still have a valid reference to C through A and B as well. So again, just following this exact diagram, we have after the create graph function ends and B and C go out of scope, and we just are left with A, the owning A in this case, then we're going to have one strong reference to B, and then we're going to have two strong references to C, and we'll go over that real quick. So all I did here was nab A from our create graph function, and so this is going to be A here, and we're just printing out A, and we're going to show, since B is an index 0 and C is an index 1, this is B and this is C, we should see that the reference count of B is going to be 1 because it's referenced one time. We clone it one time from A, and then we clone C 2 times, right? And they should all be pointing to single copies of B and C. These aren't copied around at all, which is also why we'd want to be using reference counter whenever possible. So we should have 2 references to C and 1 reference to B. So I'll go ahead and do a cargo run real quick. And that checks out. So B has 1 strong reference count and C has 2 strong reference counts. And even though B and C went out of scope, as long as the value that they contain has some sort of strong reference to it via this clone function here, then everything's fine and well. And like we said, when the reference count reaches 0, so when B equals 0 and C, this strong count is 0, then the value is automatically dropped, right? So it's just as if it was a regular value, like let equal 5, and then X is dropped after main here. So it's the same concept with strong references. So if we went ahead and did something like we made node mutable, here we still have strong references to B and C, but if we went ahead and did node.nodes equals just an empty vec, then at this point something like this is happening where we went ahead and said that, okay, we're getting rid of these references to B and C via A, and since B is no longer referenced by anything, we drop it, and we call its drop logic, which in turn, even though it has a strong reference to, or C is strongly referenced via B, since we're dropping B, we're going to also drop C, and then C is going to be nothing, and of course B is going to be nothing in this case. Now if we had like a third node over here, D, and we said, let me get an arrow out, we said D somehow referenced B, then B and C would not be dropped, if that makes sense, right? So if I went over here, we can just do, this isn't going to show a whole lot in the terminal, but conceptually, this is going ahead and we now have an empty list of nodes. So then our B is going to equal 0 here, and our C is going to equal 1, but because C is only referenced by B, we're going to drop C as well. So this gets dropped anyways. That's it for the reference counter pointer. In summary, we went over how smart pointers can perform their cleanup using the drop trait, and how reference counters allow us to create strong references to value, even if their initial owner goes out of scope, like B and C up here, and how these strong references allow multiple variables to quote unquote own a value. And again, with these values that we're strong referencing, we can't edit them. They're not mutable, right? Because otherwise that would really break things when it comes to how we understand ownership in Rust. But we're going to get into like how we're able to actually have strong references to different variables and be able to mutate them at the same time. I believe that'll be the next video, but I'll make some exercises for this video as well. I've made some for the last couple videos as well. I don't think I really touched on it in the very ends of the videos, but feel free to check out those exercises on my GitHub repo, and I'll see you in the next one.